Okay, so here we are with Stoichiometry 5 worksheet. Let's get right after it. So we're looking at the first side of this worksheet, and the purpose of it is to look at these net ion reactions. We've seen these before in precipitation, but now we're going to bring them back to acid and base. Now, before I get to these net ion reactions in acid and base chemistry, I need to speak to the previously learned material. You might have seen these double replacement reactions in precipitation reactions, because in a Regents level or a very beginning level chemistry, people will teach this type of reaction as another example of double replacement, and they're not wrong. It's another way to think of it. So you think of HI, we know that this dissociates into H plus and I negative. This dissociates as K plus. Now, of course, HI is a strong acid that we have listed in our Ka table. Okay, has a very high Ka. It's almost approaching infinity, right? And this, of course, is a soluble salt that has a what? Polyatomic ion called a hydroxide ion. So this dissociates as O negative. This is a salt. If it's in an aqueous environment, it's going to dissociate into K plus and I negative. And we know something about water. It's a terrible electrolyte. It does not dissociate very well. And you may say, well, Mr. Gradsky, I know that acid-base chemistry pH is about it auto-ionizing into, let's say, its proton and its hydroxide. It does do this, doesn't it? Well, it does, but very small amount. How do I know? The Kw, which is the equilibrium constant for this reaction, if you want to think it reaching equilibrium, is equal to 10 to the negative 14. That is a very small number. Now, what does that mean? Well, if it's products over reactants, right, it's a concentration of products over reactants, this means that this barely goes forward. There's a lot of reactants, very little products, and a huge denominator is going to equal a very small Kw, as we see. So we've been through this. Okay, so any case, if you notice something here, party people, that if we take the H plus that came from the acid and the hydroxide that came from the base, and they come together and you pour these solutions, these are all aqueous solutions, you're going to make the water. And you're going to favor the formation of water, not the ions, because the Kw favors the lack of dissociation of HOH or water, okay, into its ions. So you notice the ion from this positive hooks up with this negative. And of course, this positive ion from this electrolyte, this base that breaks apart into free ions in solution, will hook up with the free iodine ion that we should know is the conjugate base of the acid to make Ki. And so acid and base, when you do a double replacement, because this is a strong acid, it's kind of like a soluble salt, but dissociates completely into ions, and this is a group 1 ion that makes this salt extremely soluble, and of course we call it a base because it produces hydroxides. These guys are free ions, and they'll just double replace and we'll make this formula. But you know, we may think we write Ki, but really these are free ions that just spectate. So the overall reaction here, okay, because you're going to have some spectator ions, you're going to have the iodine, and you're going to have the K plus, just kind of spectating. They're free in solution. They're still free in solution, so they're not doing anything. The only thing that's really getting accomplished here is the H plus, or the proton from the acid, okay, plus the hydroxide ion from the base is making water. And we write water together always because it's a terrible electrolyte. It barely does this. So therefore, okay, we keep it together. So when you're doing a when you're doing a net ion reaction for acid-base chemistry, you got to be wary of what's strong, what's weak, and especially the water. The water is never going to be broken apart, but a strong acid and a strong base will always be broken apart into their free ions. Of course, you're only picking what's actually reacting and eliminating the spectators. Okay, remember, HI is a strong acid because the conjugate base, in this case I negative 2, has no ability to regain a proton to reform the acid. So that's why it stays undissociated, right? And of course, KOH is a soluble salt. Because of the group 1 ion and Coulombic force of attractions are so low, water can compete for these ions in a crystal to make the free ions. Okay, and therefore group 1 ions, okay, and the iodine are spectating. And it's only these guys that are reacting, and that's all we put here. Now, let me make something very, very clear. Okay, this is a strong acid. It's high on your Ka table, and this is a strong base. How do I know it's a strong base? It's a group 1 or group 2 element bonded with an OH. Those are always strong. If you look at your solubility rules, you'll see that hydroxide is soluble only with group 1 ions and group 2 ions. Now, the group 2 ions we'll talk about, there is a limiting factor to their solubility, but generally speaking, group 1, which is the alkali metals, or group 2 like calcium, okay, with the exception of magnesium, with hydroxides, are completely soluble and are strong bases. All right, completely dissociate. Now, one more point I do want to make is in our use of chemistry, very rarely do we do this type of net ion reaction. Very rarely do we have a strong acid with a strong base. Okay, it's almost useless. I mean, there are times where you might want to know how much of a base to add to an acid, sure, but in most of organic chemistry, we deal with weak acids, weak bases. Don't forget, in organic chemistry, which is about 98% of all chemistry, okay, it lives in a very, very, very narrow range of pH that won't denature proteins and allow life to happen. So we're never dealing with these very dangerous, strong chemicals that produce too many hydroxides that is caustic, or too many protons, okay, that's corrosive. So this reaction, although everyone loves to write, okay, for neutralization, is not, we almost never write this one. And somebody will, on a test, write this one, okay? Strong acid, strong base, okay, will give us H plus OH equals water. And therefore, by a lower level chemistry, an acid plus a base, a strong acid and a strong base, makes a salt and a water. But does it really make the salt, or just make a salty solution of free ions? Okay, so the point I'm trying to make here, party people, is this is a rarity. Although people love to write it, it's a rarity. Okay, so if you're writing it, be careful that you're writing strong acid, strong base. Most of the time, we are not dealing with a strong acid, strong base. This is going to be mostly wrong that I see. This is a mistake most students make in acid-base chemistry. They think that every acid and base, net ion, must be that because they learned somewhere that neutralization is about this. Yes, it is, but not every net ion will, and I'll explain that as we go down through the next one. Now, let's do nitric acid and water. Okay, now nitric acid, okay, naming acids is not part of the course, but it's helpful to know them and it makes you feel more comfortable. Nit-ic is named for all polyatomic ions that end in 8. Okay, so if I'm dealing with, let's say, the nitrate ion, nitrate, and nitrate from our tables or from memory, because you've been doing this so much, is NO3 minus 1. So party people, that 8 becomes an ic. So this becomes what? This becomes nitric acid. Okay. Now, if we have a polyatomic ion that ends in ite, for instance, this is a sulfite ion. And we can see that you would need 2 H's to add to this, just like you would need 1 H for nitric acid, right? So nitric acid, let me just make sure we understand that, is going to be NO3 minus, but the H in front. Why 1 H? Because it's -1, so you need 1 H. Okay, so there's your nitric acid. Now, if I'm going back to over here now, if I have the sul, okay, phyte ion, now ite is not 8. And we learn that ite, okay, becomes OUS. So this would be sulfurous when you put the 2 H's in front, because it's -2, so you need 2 H's. So H2SO3 would be the sulfurous acid. And if an acid is binary, like HCl, we go hydro and ic. So they'd be hydrochloric, like HBr is hydrobromic, HF is hydrofluoric, and everyone's favorite HI is hydroiodic. Yeah. Okay, so hydroiodic. All right, so in any case, we have nitric acid, okay, and we have water. Okay, well, this is an acid listed in our Ka table. It's very, very high. It has a huge Ka. It's a strong acid, so it completely dissociates. So this is going to completely dissociate, but more importantly, it's a stronger acid in H2O. H2O is listed as an acid in that same Ka table, but this is a much, much higher Ka, so big it's approaching infinity because it's a strong acid, completely dissociates. So obviously, it's going to protonate the water. And by the way, water does have two lone pairs. Remember, an H plus loves a lone pair, right? So this is going to become H3O plus. And what's left over is you're going to have the nitrate ion. That's the conjugate base. Now, this is the raw chemical formula. This is not what I should write. Let me just clean this up here. Okay. Hold on, party people. So let's get rid of all of this here just to make some sense and make sure we understand what's going on. So this, I'm just going to understand, this is basically what's happening, but this is not a net ion. And the wrong or the incorrect part of this is that I have HNO3 together. If it's a strong acid, it completely dissociates. This means you're going to have H plus and NO3 minus. So because it completely dissociates, it's not together. Okay, it's an electrolyte, just like a what? A base that's completely soluble or a strong acid, and a soluble salt. All those electrolytes, we learned that this week. So they completely dissociate. Now we do not write water, okay, dissociated, because as we keep telling you, as I keep telling you, I don't know who we are, but as I keep telling you, it's terrible at dissociating. Why? Because its Kw is so small. So I have to keep that guy together. So when you think about both sides, this guy grabbed a what? H plus, became H3O plus, and if you notice, we have NO3 on both sides, and therefore you can see that it spectates. Get rid of the elements not doing anything, and what do I have? I have an H plus plus a water, making H3O plus. And so let me just put that here so we can cherish all that. And sometimes it's easy when you do these to write out, the chemicals normally and then realize what is a good electrolyte, what's not. So this is clearly going to be just an H plus the water. It's a neutral compound, making the hydronium ion. That's it. The NO3 minus doesn't do anything. Why? It's a conjugate base of a strong acid. If it could do anything, it would pull H's from water, but it can't reproduce the base or make any hydroxides because it is a spectator ion. Why? Because for reasons we've learned, nitrate is 4 atoms. That's -1. It's 4 atoms sharing a -1, which means its Coulombic attractions are low, right? The diameter is too big for -1. All those things are still in play. Okay, moving on to the next net ion reaction. And this is more realistic, really is. Okay, this is more like what we're going to see here. Yes, we can have a strong acid in water, and this is the net ion here, but this is the magic one. This is the one that comes up more in our chemistry, more in real life chemistry, because again, if we're going to be dealing with most of the reactions that occur in living type of organisms, if 98% of most reactions are organic, then the organic type of reactions would support, of course, life, and life only exists in a narrow range of pH. You can't have strong acids and strong bases. Normally, there are some instances, like in the parietal cells of the stomach. But in any case, so what I have here is HC3CO2. This is acetic acid, or as we'd say in West Hampton, vinagre. Okay, or we should say vinagre. Okay, now what does it look like? It looks like this. Carbon, double bonded to an O, single bonded to an O to an H. It's called a carboxylic acid. And this is hooked up with another carbon, which, okay, is going to be 3 H's bonded to. Okay, so this is vinegar or acetic acid. That's its name. And why acetic acid? Why acetic acid? Because ic came from a what? Came from an 8. So 8 comes from the ic. So this is the acetic acid. So if you look in your table, this is the acetate ion. If you take this and take this away, this will be negative when it's an ion. If you look, it's CH3, COO negative. That's listed in one of your tables as the acetate ion. Sometimes they'll list it like this, C2H3O2, and that's the acetate. What did I teach you? 8 becomes ic, so that becomes acetic acid. So, and just a little aside there, as I do naming, I'm not going to hold you accountable for naming, but it does make your life easy if you know what the naming. But the bottom line is, if you look at your table of Kas, acetic acid, however it's written like this, it does have some different ways to be written, is not not a strong acid. It's a weak acid, and that's really important, party people here. That's a weak acid, and this is more like the chemistry we're going to do. Why? Because we have a lot of weak acids, okay, and a lot of weak bases in our chemistry, organic chemistry. Now, why is this really important? Well, because if it's a weak acid, you should realize that it barely dissociates. It barely dissociates. So if it barely dissociates, and this is important, if you look at your Ka table, you'll see that if you're not a strong acid, you're a weak acid. There's nothing in between. So acids that are weak barely dissociate, which means they're terrible electrolytes, just like water. So I would never write this acid out as its free ions. So I'm going to write it together. So H in front, and I'm just doing that to remind you that it's an acid, CH3, CO2. Again, what they're doing is they're saying this compound, CH3, CO2, and they're putting the H in front here to remind you that's the compound. So this part here is where this part here is. Doesn't matter. There's many ways to write it. But I don't write it broken up. I write it together because it doesn't dissociate very well. Only strong acids, only strong bases, only soluble salts are electrolytes. Hey, okay. What else do I have? A hydroxide ion, which could be delivered by a strong base. Booyah. Now this is really important. Weak acid and a hydroxide is a strong base. And what's going to happen is the strong base is going to drive this reaction forward to completion. And that's really important. We can do stoichiometry now if we have a weak acid who barely gives off H's. But this strong base will make this weak acid feel like a strong acid. It'll pull every single H off as long as there's enough OHs. So this is going to pull this H away that normally doesn't come off very easily, but it does. Somewhat. This OH will pull it. And of course, you're going to make water, which I do not write as broken up because, again, for reasons we explained. What's left over? CH3, CO2, and negative. This is the conjugate base of this weak acid. So in this case, as in most cases, party people, all right, as in most cases, you're going to have a weak acid or a weak base with a strong acid or strong base. You're going to have a combination like this to drive the reaction forward. Okay, case in point, in the stomach you have HCl. We have special lining in the stomach with mucus to protect our stomach from being corrosively broken down by the hydrochloric acid, which is there, of course, for protein digestion in our stomachs. Now, this stomach is connected to a sphincter, and sometimes, and this opens and closes as the esophagus brings food down. But what happens sometimes is some of the acid does move back up to the esophagus, which, by the way, is behind the heart. And so it makes you feel like it's really hurting here. It's called heartburn. So we take antacids, and the antacids we drop are not strong bases. If they were, they would do what? Break down the esophagus, because a strong base with too much hydroxides is dangerous. So what they take is they take weak bases that barely interact with your esophagus. And when they hit the strong acid can be neutralized by a weak base because the strong acid forces the weak base to completely act as a base. And that's what we're going to be doing the rest of this unit. We're going to force weak acids or weak bases to go to completion and not have equilibrium, because these guys normally reach some kind of equilibrium position, whereas a strong acid, strong base do not. We're going to drive these reactions. So you're not going to see, very rarely, this reaction. And I'll tell you what, people are going to write this every time because it's drilled in their head in easier classes. This is more like what you're going to see. Next one, NaOH, hello, strong base. So I'm just going to write the hydroxide. The Na plus is a spectator. There's a weak acid, the same weak acid we had here. Okay, and if you notice, it's the same half reaction. Not sure why I did that, but hey, I'm tall. HCH3, CO2. And of course, weak acid, strong base, And I guess this is going to yank, I definitely know it's going to yank this H away, because a strong base will make this weak acid feel like a strong acid. It's going to yank as many OHs. As long as I have enough OHs, I'll yank every H away. I'm going to drive this reaction forward. Notice no what? No double arrow. So we're going to make water, which I write together, weak electrolyte, and I write the what? The conjugate base. All right? And that's what I put there. And that's my overall net ion reaction. It's the same as this one, except I added what? NaOH. Notice there was no Na plus on this side or this side, because it would spectate. I got rid of my spectators. Also notice that the charges on both sides are the same. -1 plus is 0, -1 plus is 0, -1 on both sides. Okay, so it's important. This is a driven reaction, stoichiometrically driven by the strong base. Okay, how about ammonia, which is a weak base? How do I know it's a weak base? It's not a group 1 or group 2 metal with a hydroxide. Hydronium, H3O plus. Now we can treat H3O plus. Remember, we said it's synonymous with H plus. Okay, so that's from a strong acid. So we can treat an H3O plus as a strong acid. This is a weak base. Hello. Okay, the strong acid will make the weak base act like a strong base. So what's going to happen is this is going to give it a proton. It's become NH4 plus ion, and this becomes a hydroxide. All right, and this doesn't associate, right? And neither, we can write this as synonymous. So that's basically what we have here. And that is the net ion reaction, kind of like a weak acid base equilibrium. Now, we were drawing these before in class this week because we had a weak base, a weak acid here, but a strong base is going to drive this reaction forward as long as I have enough of that to make this weak base grab onto every H plus. Remember, to be a base, you grab electrons using your lone pair. At least that's how nitrogen works. But it's not a strong base, and not all of it does that. But H3 plus will force, okay, its H pluses onto the weak base and make it completely get neutralized and work its way forward. All right, so that is the first side, and that is going over, okay, basically how to write net ion reactions with different acid bases, okay, weak or strong.